Welcome to class number 1, session number 3. In this session, we will continue what we have already started in session number 2 of class number 1. Two-dimensional structures include thin films, planar quantum well, and superlattices, as could be seen on the screen. As a representative example of thin film, please have a look on scanning tunneling microscope image of a self-assembled monolayer of N-decanthiolate on gold surface. As seen in the image, the individual molecules closely packed into hexagonal array. Also, besides that, one can see clearly the features of the assembly and the surface, namely, one can see domain boundaries, which are highlighted with light blue strips on the figure, and one can see also gold vacancy islands, which can be seen as circular blue spots. In the lower image of the screen, you can see a transmission electron microscopy image of a superlattice, where alternate layers of two different materials exist. In this context, please note that the thickness of each layer is only 2 nanometers in thickness. One of the major groups in two-dimensional structures is thin film, namely two-dimensional film with a thickness that ranges between 1 to 100 nanometers. When films are very thin, their electronic and optical properties deviate substantially from those of the bulk material. As the material is miniaturized towards the nanoscale, the confining dimension naturally decreases, but the characteristics are no longer averaged by the bulk. The energy spectrum becomes, in this case, discrete and measured by quanta rather than continuous as in the bulk materials. The confinement of the electrons that exist in these systems change their interaction with the electromagnetic radiation significantly. Electrons are confined in the direction that is perpendicular to the substrate and thus affect the wave function as well as the density of these states. Similarly, phonons that are confined in the direction that is perpendicular to the substrate affect, therefore, the thermal property. All transport phenomena in the two-dimensional structures are highly affected by defects, boundaries, and interfaces that might exist in or at the vicinity of the thin film. More details about all of these effects will be given in the next classes. Now we will move to the three-dimensional structure, which include bulk nanocrystalline as well as nanocomposites. Nanostructured bulk materials include several subcategories, which are mentioned in the following. The first subcategory is crystalline materials. In this category, the atoms, molecules, or ions which make up a material are arranged in an orderly repeating pattern. In some cases, the regular ordering can continue unbroken over a large scale, such as in the example of diamonds, where each diamond is only single crystal. The second subcategory is called polycrystalline materials. Solid objects that are large enough to see and to handle are rarely composed of single material, but instead are made of large number of single crystals known as crystallites, whose size can vary from a few nanometers to several meters. Such materials are called polycrystalline, as mentioned previously. Almost all common metals and many ceramics are polycrystalline in their properties. The third subcategory of this material is called amorphous materials. This category, which we call also non-crystalline solid, is a solid that lacks the long-range order characteristic of a crystalline. Indeed, amorphous materials have some short-range order at the atomic length scale due to the nature of chemical bonding. Such solids include, amongst the rest, glass, plastic, and gel. Now we will move to the nanocomposites. A nanocomposite is a multi-phase solid material where one of the phases has 1, 2, or 3 dimensions of less than 100 nanometer. In the broadest sense, this definition is more usually taken to mean the solid combination of a bulk matrix and nano-dimensional phase differing in properties due to the similarities in structure and chemistry. The mechanical, electrical, thermal, optical, electrochemical, catalytic properties of the nanocomposite differ quite significantly from those of the component material. Size limits for these effects have been proposed in the scientific literature and include, amongst the rest, the following. Composites with less than 5 nanometer nanomaterials are designated for catalytic activity. Composites with less than 20 nanometer nanomaterials are designated for making hard magnetic material, and composites with less than 50 nanometer nanomaterials are designated for refractive index changes, and finally, a composite with less than 100 nanometer nanomaterials are designated for achieving mechanical strengthened or restricting matrix dislocation movement. Nanocomposites might include combinations of organic material and organic material. It also can include a combination of organic and inorganic material, and finally, it can include a combination of inorganic and inorganic materials. This large amount of reinforcement surface area means that a relatively small amount of nanoscale reinforcement can have an observable effect on the macroscale properties of the composite. For example, adding carbon nanotubes improves the electrical and thermal conductivity. Other kinds of nanoparticulates may result in enhanced optical properties, dielectric properties, heat resistance, or mechanical properties such as stiffness, strength, and resistance to wear and damage. We will come now to the end of class number 1, session number 3. Thank you.